Very good. So, so I have took the liberty of changing the order of presentation. So the construction of infinite interacting particle systems I'll leave for tomorrow. Today I want to focus on more basic questions, the construction on finite state space Markov chains. But before I start, I want to thank all of you for coming here, whether you're watching it on Zoom or on YouTube, and wherever you are, welcome to this talk. We're very happy to have you here. If you have any questions, let me know. And I want to thank Andrew and Sunil for organizing for us this nice series of lectures for all the members of the PiNE group and the LMS, the London Mathematical Society, for supporting this event. So what I'm doing today is the first of 3 lectures dedicated to the study of interacting particle systems via martingale methods. Right, so I want to talk to you about finite state space and some basic tools as it's in the title. But while I was preparing for this talk, I took the opportunity to go back to the foundations of these very classical books with the hope to get and transmit the overall picture of the field. And this was basically encouraged by the fact that we have a very nice understanding of what's happening on the finite states, on the finite case. We have, when we have an irreducible stationary Markov process on a finite state space, we have a rather complete picture and a very satisfying one, actually. However, the problem of moving these interpretations beyond the finite state to deal with infinite cases meets a series of difficulties and challenges. Though they are very fascinating in themselves, they put our imagination to a very hard test. So I'm going to follow the advice from Liggett in his book from 1985 that is important not to get bogged down in the first chapter. So I have opted for a more soft approach, basically starting from the finite case, making some allusions as to what happens in the infinite case. And then in the next lecture, I want to say a few words about how to construct infinite interacting particle systems. All right. So the overall picture, the outline of today's talk is the talk is divided in 2 parts. The first one is the construction in the finite case. So our focus here, let me see if I can write, yes. Our focus here will be on the finite case, but I want to say a few words about the infinite case and in particular interacting particle systems. So, and I want to conclude this first part with an overview that, even though it's incomplete, so it's a partial overview, I think it's helpful to look at it to get a sense of what type of questions we're interested in asking and where we're going to. So that's the goal of the first part. Second part is more heavy on the mathematical proofs. I want to talk about Kolmogorov equations, both the forward and backward equations. It's the most analytic part of the talk. Then I'm moving to more probabilistic tools, martingales and martingale problems that really show their true strength when we combine them with some criteria for tightness that allows us to identify limit points of a family of Markov processes. And in conclusion, I want to say a few words about how these tools come into action, these three tools. So the panorama is a recapitulation of all these tools and how they combine. Right. There are more tools. There are certainly more tools. For instance, coupling and duality that I'm not mentioning here, but Liggett says they are very important and has devoted entire chapters to the study of coupling methods for the study of interacting particle systems and so on. We'll see a little bit about coupling in the next talk, but for today, these are the basic characters that we're going to see. Okay. So the basic property that characterizes Markov processes is the probabilistic analog of a familiar property of dynamical systems, namely that the present state of the system contains all the relevant information concerning the future. So we do this in a probabilistic way, meaning that we don't have a specific knowledge about what's happening to the trajectory, but with the laws, we then do have a complete description of the evolution of the laws. So continuous time Markov processes in finite state spaces, they they are based. What I want to divide the description of this process in two steps. First, the construction of the skeleton, and then the construction of the instance of times that we jump. So for now, let me assume for now that we're jumping at time t. So you can see here the finite state space I have numbered from 1 to n. It's worthwhile saying that we could have named otherwise. We could have, some people do, just name them 1 to n. It doesn't matter the name you give to the points. What's really important is the way that you're jumping, is the probability, is the transition probabilities. This is really all that matters. Up to a bijection, it's what's in a name here. It's arbitrary. The reason I've chosen x is that this is a good name for a random variable. So that's why I'm using x, but some people use I and j, and that's just as well. So if at time t we have a jump and we're starting from configuration I, how do we continue? So basically what we do is that we throw a dart that is a uniform random variable from between 0 and 1, and we have a partition of this interval according to the transition probabilities we have assigned from site A to site J, and depending where the dart lands, that's where we're jumping to. Okay, so if we collect all the transition probabilities into a stochastic matrix, we have the full description of that controls the evolution of these probability measures. And this is the stochastic matrix PT here. I'm allowing the term P because I'm allowing the transitions to depend on time. That's just the starting point. Truly, what makes this stochastic matrix a stochastic matrix is that all its entries are positive and the rows add up to 1. So it's important that they add up to 1 so that we can make a partition of the interval and know for every point where we're jumping to. These boundary regions you can specify to belong to the set on the left. And if you want, just to avoid ambiguity, you have to make a difference in the last one. But this is a zero measure set. It doesn't make too much of a difference. You're free to choose how you want to decide the jump. So it's not that important. Right. But for our purposes, we will drop the dependence in time because we're talking about time homogeneous continuous time Markov processes in finite state spaces. Right. So I want to tell you how we construct these processes in time, because so far we were talking about the sequence, the chain of events, right? So I want to, there are many constructions, many interesting constructions. They give us different views on how these processes are assembled. I have separated to begin with two, that one that I call wait and jump, and the one that I call follow the clock. Basically, wait and jump requires us to have two families of random variables. They are all independent. We have standard exponential random variables and uniform random variables, and we need to have the rates at which we jump from point X. So these are real numbers between 0 and infinity, positive real numbers. Construction is inductive. We start from an arbitrary point at time 0, and given that we have constructed the chain up to the kth jump, the next one is determined as follows. We look the value of the exponential random variable of the kth step. We divide this by the rate of the configuration we are in. So we know what's the value of x k. And we add this time to the total waiting time that we have to determine the next instant that we're jumping. Where we're jumping to is a different question here, and we decide that upon throwing the uniform dart or looking the value of this uniform random variable, and using the stochastic matrix P, we decide where we're jumping to is exactly in the same way that we did before. There are many ways of doing it. You can partition the interval as long as you keep the probabilities compatible. It's a good way to do. Right, when we put all of these transitions together, we have created a trajectory in time. This is a right continuous trajectory with left limits. So that's the basic construction of a continuous time Markov process. And if you have that, you have already specified the construction. So I was talking to Ostap, and he said, well, you should note that this algorithm is a very classical one, was known to Kolmogorov, and is referred to as the Gillespie algorithm or the Doob-Gillespie algorithm. I had never heard, but he pointed that out, and I think it could ring a bell to some of you in the audience. It's the Gillespie algorithm, right? The follow the clock can be also familiar to you and have another name, I don't know. But basically what we're doing is that instead of having a uniform random variable, we're just using exponential random variables. So at each step, at each site, we have n independent exponential random variables with different rates. And what we're going to do, we're going to follow the first clock. So these exponential random variables, they can be thought of as clocks. So when the clock rings, something happens. We are going to follow the first clock that rings. The construction again is inductive, and we look so this is the first clock that rings, the first site associated to the point that we're sitting in that rings. So it is the smallest value of all the collection of n independent random variables. This is almost surely unique, and that determines where we're jumping to, and at the same time the instant that we're jumping. So with that, we have constructed in another way a right continuous left limits trajectory that is dependent on the values of these exponential random variables. So these two constructions actually induces laws of probability in the space of Cadillac trajectories. So Cadillac is a French acronym for right continuous with left limits. It's a short way of saying it. The point of these two constructions is that if they are compatible in the sense that the individual rates can be related to the global rate and the probabilities in this form, then these two probability laws are the same. So we have created in two ways the same law in the space of trajectories, and that's what we're looking for. Right, we're interested in the laws. So before moving on, I want to show you a couple more constructions. So this is the graphical construction. It's based on Poisson point processes, which are very closely related to exponential random variables. Basically, what we can do is we can superpose colored Poisson point processes independent and with rate rxy. And from the reading of the color, we know where we're jumping to. So here I have, instead of using x1 to n, I have used colors to refer to the states of our system. You can see from the relation of Poisson point processes and superposition of Poisson point processes and thinning or coloring of Poisson point processes that there is another way to construct these processes by using something that's closer in spirit to what we've done with this wait and jump or Gillespie algorithm. Right. The point is that all these constructions are equivalent. So we have seen 3, 4, and there are more really. The reason I've chosen this one, this last one, is that it gives us a very nice perspective on how it looks like, how trajectories look like. It's important to say that since they are right continuous with left limits, these intervals here are open, and at the instant of transition, we are choosing to be already in the new site. So this is a convention, and we could have done otherwise, but it's conventional to assume they are right continuous and have left limits. Right. So if you have any questions, let me know. I want to move on to another construction, which is a more intrinsic one, which is some sort of an answer to a natural question, which is, well, there are different ways of assembling the random variables, but we're really interested in the laws they induce in the space of trajectories. So is there a construction that is more intrinsic? And it's already hinted here in the slide that there is. And the way to go is to consider operators that we call the generator that acts on the space of bounded continuous functions of the space. Let me just say that on finite state spaces, finite discrete state spaces, every function is bounded and every function is continuous. So we could think of this as a matrix acting on a set of vectors. It's just as well. But it's good to keep this framework because it translates better to general cases when we move beyond the finite case. And that's the interest in having this notation. If you look at the generator and you have never looked at one first, it may seem a bit strange how it builds the process. So it's good to be able to read the transition rates and the exponential clocks because they are more tangible ways of representing the dynamics. So here we see in the brackets that we have a jump from x to y with rate rxy. So if you read this and you say, well, now I know what is the rate of my exponential clocks, I can build the process. And you could proceed like that. But the way we want to do here is using the generator to build a semigroup. And this is done by taking the exponential of this matrix. In the case of finite case, is a matrix, but it's in general an operator, a bounded operator. If it's bounded, sometimes we can do it without being bounded, but there are some technicalities. Basically, we're summing here from n positive, including 0, and this sum is convergent, so it's well defined, the action of the semigroup on the functions. And the point is that this also defines an action on the space of probability measures, and the definition of this action is by duality. We identify the measure, the evolution by t, by t seconds of our initial condition using this inner product. And if this seems strange at first, remind that the indicator functions are bounded and continuous. And if we write mu t y, this is actually the probability that mu t is assigning to the set y. So having a finite set really is explicit what is the measure determining family that we're interested in looking at. But we can also interpret this as the probability starting from mu0 that at time t we are in y. So the reason for stating this construction in the space of continuous bounded functions is that for non-uncountable spaces, say R or product spaces, the family of the measuring determining set, the indicator functions are not enough. They do not give the description we're looking for. And so we need to go beyond that. What we have done so far tells us how we evolve the measure across a certain time interval. But we want to build a trajectory in the space. We want to build a random variable in the space of trajectories or a measure in the space of trajectories. And to complete this construction, we need to do a Kolmogorov extension using the Markov property. So we can make a consistent family in the cylinder set. The Kolmogorov extension leads us to a product space. Basically, we go to the space S to the power 0 infinity. But here, the trajectories have no property as we cannot say trajectory is continuous. These are not allowed. These questions are not allowed in our sigma algebra. So to complete the construction, we need to do a regularization. So this is rather technical and can be found in the books from Hevuz and Yor. But basically has to do with relating the resolvent and some class of semi-martingales that is enough to capture discontinuities. And then we can select a modification of the process that we define in the canonical space and obtain the construction on the space D. Right. So now we have seen 4 or 5 different constructions of processes. So let me say a few words about what happens in the infinite space. For the infinite state space, the challenge really is to deal with the unbounded transition rates. If the transition rates were all bounded, we could continue using the idea that we had for weight and jump. We throw an exponential random variable and then we consult the transition kernel to see where we're jumping to, and we could build the chain all the way. But if these values go to infinity, then we really need to be careful with what happens. Because let's say we jump from n to n plus 1. Let's consider a pure birth chain that jumps from n to n plus 1 with rate n squared. So basically, the expected value of the nth jump is 1 over n squared. And if you see the sum in n, this is finite. That is telling us that we will see in a finite time infinitely many transitions. So we are going from 1 to infinity in a finite time. That's called explosion. And the reverse process could be naturally referred to as implosions. And I heard in the corridors that's actually a good name. We should call these things implosions. And what happens is that we go from infinity to a certain value in an instant. We enter the space in an instant, and then where we're jumping to after this point is just following a chain of events. But in either case, if we have explosion or implosions, we have broken the sequence, the sequence of events. So the way to solve this is to deal with constructions up to explosions, in the case of explosions, or to deal with an approximating sequence, make the construction via limits. And that's what we do in the case of interacting particle systems. And I want to say a few words more about interacting particle systems because they have their own notation and they are subject in themselves. All right. So our state space is now a product space. Basically, is the motivation is motion of atoms in different regions undergoing reaction or simply diffusion. So we're trying to understand the evolution of these configurations. And instead of naming them as X and Y, now we reserve the value X and Y for sites, that is, points in space. And if we take, for instance, eta X, this can be a value, for instance, 0 or 1. If it's a spin model, it could be any value. And sometimes we have multiple values. Could be also in a compact interval 0, 1, or we could also allow this to be in R. So there are many. So I was specifically vague about what is this spin space, the space of projections in a site, because it really depends on what we're modeling. And the point is that in the finite case, for instance, say we are trying to follow a gas, the state of a gas over time. So we're going to divide space and make a exclusion assumption. So the exclusion is that there are no particles superposed in the same region. So a region is either occupied or empty. So when you think about it, this requires you to have many, many regions because typically a gas, the number of particles that we're looking, so n is the number of sites, n should be larger than the number of particles, which is of the order 10 to the power 23, which is the Avogadro number, right? So if you think about this type of models that we're doing, the number of configurations we have is 2 to the power n. This is a huge number. And the matrix is typically very big, but very sparse. So the transitions we observe are from one cell to a neighboring cell, local dynamics. So it's a transition matrix that's full of zeros. So once we specify these local interactions and the local transformation maps, just for concreteness, let me write 1, let's say gamma x plus of eta is also written as eta x plus. This is more familiar to some people. That's eta plus delta x, which is the addition of a particle at site x. So if we're talking about reaction, we can add or subtract particles. Another common transition is x jumps to y. So we add a particle in y and we remove a particle from x. So these are typical local transformations that we'll consider. More details on that will come on the next talk. So the idea is that we specify the transition rates and we can write the formal generators, but now we're not summing over all possible states. We're summing over all possible local transformations. It's the same, but it's a shorter way of writing the transition, the generator. So I have written here formal generators because in the case when we could be typically interested in the case where V is the entire, is a discrete but infinite but countable space, then we're dealing with an uncountable state space. So what happens here is that there are infinitely many particles in the system, and infinitely many particles are making a transition in a finite interval, in a finite time interval. So it's like implosions all the time. The transition rates for individual particles depend on the entire configuration. So it's not clear if this specification in the local dynamics determines the evolution of the system in a unique way. So before we continue, we need to examine this question of existence and uniqueness of these processes. So that's one of the key challenges that we have ahead of us. So, but now I want to conclude the first part saying a few words about what we're after, what we're typically looking for. So I cannot, I think this is a very good picture. It gives a lot. The more you look at it, the more you learn from it. At least that has been my experience. So basically what I have written here is the master equation. It's called the master equation because it explains the evolution of the probability measures in the space. So continuous time Markov process defines an evolution in the space of probability measures. And that's what we're after. We're after a picture or an explanation of how these processes evolve. So as Hugo was saying, irreducible processes living in a compact space will typically be ergodic and have a unique invariant measure. So the invariant measure is a fixed point of the system. And what we look at is if we start from different configurations, we want to know how long it takes for us to converge. So that question that Dublina asked before, if we have a uniform condition, are we converging at an exponential rate to the fixed point? So these are typically interesting questions that we want to have to give an overall picture of convergence in this setup. So it may well happen that the system pretends to converge to a certain state. Let's say it goes to a certain state, stay there for a long time, maybe orbits a little bit, but eventually is going to the unique fixed point. So these states that they trick you into thinking that they are invariant, but they are not. They're called metastable. So metastability is actually when the system tricks you into thinking it's converging to a certain point, but actually it isn't. Our goal in the end is to understand the behavior of these processes in all relevant scales. So maybe we're not interested in the long-term behavior. In the long term, well, maybe we're not there anymore to check. We are interested in what happens in a certain time horizon. And that's what is the challenge of the description of these processes, to give a reasonable picture of convergence or a good description of what happens at all relevant scales. All right. So to conclude this first part, I want to make a list of interesting questions that we ask. It is already very interesting to say what happens for certain test functions, say what happens for the first moment, the second moment, or what's happening at certain region. Sometimes we're interested in a specific class of test functions, so we don't need to give a full description of the process. Another interesting question that we may ask, sometimes the systems are not irreducible, so we have many invariant measures. We want to understand what are the set of invariant measures of the system and how we converge to them. So, but in the case of having multiple families describing the same macroscopic phenomena, we want to be aware of if we can make a space-time rescaling and capture the properties of the system at the appropriate level. So this is also one of the questions that we ask. So it's important to say that what drives the evolution of the field is an attempt to explain physical phenomena that now belong to the realm of statistical mechanics. So for instance, how do we make sense of fluid equations? How do we make sense of the smooth flow of fluids in an atomistic world where we cannot expect from a microscopic point of view that this smoothness still holds? So that's a big question. Another question that motivates our investigation is to understand what is the state of matter. For instance, if we single out an atom of water, can we say it's solid, liquid, or gas? Or is it the state of matter a property that belongs to the collective interaction of those particles? And more, if that's the case, can we learn something about phase transition as we study, as we get a better understanding of the state of matter and of as our models of the physical dynamics improve? So these are driving questions that motivate us. And but actually, as time passed, it became clear that models with very similar mathematical structures can be formulated in other contexts. So we can use interactive particle systems for other types of problems. For instance, we can study neural networks, tumor growth, we can study the spread of infection and other behavioral systems. So there's a wide class of problems that now fit and belong to interacting particle systems. So it's a very, there is no lack of questions in this field. So it's a very vivid area of mathematics. So with that, I conclude the first part, and I want to move now to the study of the tools. Right. So let me just list what are the tools that we're going to see. I already spoke in the introduction, but it's good to say that we're going to look at the Kolmogorov equations, which are the most analytic ones, both the forward and the backward equation. Then I want to talk a little bit about Dynkin martingales and martingale problems. But in between, I wanna say a few words about tightness. So I'm going to give more formal proofs about Dynkin martingales and martingale problems. But I want to say a few words about these other tools as they complete they are not an exhausting list, because I've opted not to talk about duality or coupling methods. But I want to conclude with a few words on how these three act together to allow us to say something about limits of interacting particle systems. So that's the goal for the second half of this talk. Right. So the Kolmogorov equations, I am going to describe them in the context of diffusions. So it's not exactly, it's not really a finite state space anymore, but it's important enough because it relates a family of partial differential equations with diffusions, showing that diffusions are actually some basic solutions of these problems. So the forward Kolmogorov equation, I always get confused about why is it named forward. You can recall it because the derivative is happening on the forward variable. Conditioned on the fact that we start at time s from x. So this is what's written here. That's the initial condition, right? And we want to know the evolution of these measures. Very much related to that picture that I showed you with the master equation. So the forward Kolmogorov equation sometimes is also referred to as the master equation. I think they have their names depending on how you're looking at them. The way to make these equations formal is to use a family of test functions. So let phi be a test function, and we write the conditional expectation of this test function v that depends on t and x. So the derivative in time, we can exchange. If you're generous with me, you allow me to exchange the integral with the derivative in time. And on the other hand, we can apply the Chapman-Kolmogorov equations to examine the difference. So basically, let me just say that we are jumping from s, at time s to time t, we jump from x to y, but from time t to time t plus h, we jump from y to z. So to jump from x to z in the interval of time s and t plus h is the same as jumping from x to any y and then jumping from this y to z. So that's what's written here, and we have and we are able actually to take the limit inside. So thus far I didn't exchange limits, but we're able to put the limits inside and recover the action of the generator on the test functions. So at this point, we usually assume that we can make an integration by parts and transport the action on the function to the action on the measure, which typically has a good coefficients. And if we can do that, if we compare these two equations here, this and this, they integrate the same for all test functions. This means that these two objects here, they are the same. That's how we derive or formally understand the forward Kolmogorov equation. Right. So it's important to say that there are some problems with this derivation because we're tacitly assuming that it admits a density, and we think of the forward equation really as a function on the densities. And even when all this is justified, there is the difficulty of interpreting the adjoint, and they are only really legitimate when the coefficients are smooth. And for this reason, we turn to the backward Kolmogorov equations that make less, they are less restrictive and give the same picture. So the backward Kolmogorov equation is a time reversal statement of the problem. So we know the final, that at time t, we know we are in x. And we have this minus sign to reflect that derivative in time is reversed. Is backward because it's acting on s. And the way of making this formula is, again, using test functions. We put the derivative inside. Again, that's just a manipulation. But the derivation in time using the Chapman-Kolmogorov method gives us in a very straight way the action of the generator on the function w. So now, if you allow me to pass the L from w to put it inside here, the integral, you can kind of make sense of how we get this formulation here. Actually, the full derivation is more involved, but I think that gives us a way of remembering it, or making it memorable and ready to use. So these are the two equations, and that's the analytical connection that has very ambitious goals. So if we can say what's happening with these measures at all times, we have in principle answered all the questions we could possibly ask. But this can become very difficult. So it's good to have other tools. And I'm going to move now to martingales. That, as Hugo said, these martingales are invariant objects that keep their expected value constant. So they are easy to deal in the sense that they are constant over time. So I want to show you a family of martingales that are called Dynkin Martingales. And the first one is basically the difference between the observation of a certain smooth function. So f here is a smooth function that may depend on time. And we are assuming that its derivatives for first and second derivatives, they are smooth. So this is the observation. And what we're subtracting here, oh, sorry. Oh, I shouldn't have done this. Let me go back. Oh, no. Okay, so let me forget about this. Actually, the plus is here. So this is a minus. All of this is what we can call the prediction. So the prediction is the best guess we have for the evolution of our system. So L is the infinitesimal generator, tells us what we expect to see in a small time, in what's the change that we expect to see in our probability measures. So if you subtract the observation from the prediction, and if it's, well, a good prediction, we expect this to be essentially a martingale, or to have zero mean. And the next martingale here, this NF, tells us what is the variance of our prediction. So it tells us how much we should trust our prediction. So this object here, the Q, is the Carré Duchamp, which is very closely related to the generator. It captures the infinitesimal evolution of the square difference, right? So that's a way of expressing the quadratic variation operator. That's easy to compute, because sometimes you don't want to compute this difference here compute many times the generator. This is too difficult. That's the formula you want to look at. This is handy. But the other one is better for some theoretical purposes, basically because it's more simple in the sense that it only depends on L. It does not make reference to anything outside of the generator. And also because, as we'll see, appears in the proof. So now what I would like to do is buckle up. I want to give the proof that why these are actually martingales. So to show that they are martingales, basically what we want to show is that the expected value is zero, of this difference is zero, right? If we show this, we will have proven that it's a martingale. And the proof is somewhat straightforward. We want to show that the function as a function in time is constant. So at time s, we know it's zero because it's the difference of the object and itself. So ms minus ms, that's zero. And for r larger than s, we want to show that the time derivative is zero. So to do that, basically using the smoothness of the functions, we can recover that from the integral part. So I'm actually looking at phi of r plus h minus phi of r 1 over h, right? And I am separating the analysis first in the integral part and then the difference of the f's. So first the integral part, that's the fundamental theorem of calculus. We recover this straightforward, this object. The next one is a bit more, it's not too much, but we have to add and subtract the term. So here was plus h, it's a typo, I'm sorry. So what we add and subtract is the value of the function only changing in time, so that we can take limits separately. So let me put here a plus h. Right. And we see that these two terms that appear, these for the first limit, we have used the smoothness conditions, and the second one for finite state spaces, that's automatic, that holds all the time for our continuous time Markov processes. So we see that they will cancel out because we have this minus sign here. So these and these, they match and they cancel out. So we get that the first, the prediction, the observation minus the prediction is a martingale. The second, the proof that the second is also a martingale is a bit more complicated, but I want to try the challenge of explaining it to you in the time that we have. So first I will be using the notion of equivalence of two processes to mean that their difference is a martingale. And what we're going to do is a sequence of replacements and to show that this difference is a martingale. Okay, so it will also be important to recall the formula of integration by parts. And if you don't remember, let me just say a few words. So G is a finite variation process and MT is a martingale. So let's, it's okay to assume here that G of 0 is 0. So we can subtract this here. And actually we can sum this over an arbitrary partition. Tk minus 1, mtk minus 1. And we can write this difference here as the sum in k of g tk m oh sorry, GTK minus GTK minus 1 times MTK plus the sum in K of GTK minus 1. This is not here, this is here. MTK minus MTK minus 1. The partition is arbitrary, so we can refine it to converge to this formula here. So that's the formula of integration by parts. It's worth saying that this is coming from this, and that's a martingale. We have used the G here at the initial time, so it actually cancels out when we take the expected value. So the first application of this integration by parts formula is with this expression here for the martingale M, compensating for the initial value. So you see that this is M R, and this is D G. So this is M of S, sorry, this is M of S, this is DGS, and that's our GT, right? So I hope, yes, so that's an application of the integration by parts. So when we square the martingale M, we have, that's simply an equality. But now we can start using, so this formula here comes from the application of the first part, because we learned that this is a martingale. This is the Dynkin martingale associated to F squared, right? So if we put a squared here, we have, the square is here, right? So we can replace already this term here using the equivalence of, using this equivalence, we replace here. And the next part here is just an equality. We have rewritten F in terms of MF0. So that actually has a -2 that multiplies this minus, gives us a +2. We had only one plus, so we have to subtract 1 to go back. So the next step in the proof is to write the formula of integration by parts that we have for this object here. So they open up like this. You can see I have separated them because I want now to call your attention to these two terms. If you look at it, that's actually GT squared is equal to 2 integral from 0 to t gs dgs. And this is our GT. This is GT squared. This is our GS. And this is our DGS. So they cancel out. We can cancel these two. And what's also possible now is to cancel these two here because of the chain rule for the derivative. And we end up with the formula for the quadratic variation. So, okay, there you have it. That's the proof that the Dynkin martingales have that specific variance. That's the formula for the quadratic variation of the Dynkin martingale. So these are very useful. They are very useful and worth looking at it at least once with all details. I've taken most of the argument from a book from Kipnis and Landini, and you can see this in the appendix of the book. So now I want to say a few words about tightness, not going to enter too much in detail. But when we're dealing with a family of processes that are modeling a certain macroscopic phenomena, we want to know whether we can take a convergent subsequence and whether the sequence itself converges. So the first stage, the first question we really ask is this family tight, or is this family pre-compact? So there is a criterion for pre-compactness, which is tightness, that consists of showing that most of the mass of our family is concentrated in compact sets. So no matter how much we want to have, there's always a compact set that concentrates most of the mass uniformly for all our processes. So I want to say that this K here is a compact set in D, the space of Cadillac trajectories. It's not a trivial compact set. It's difficult to understand compact sets in the space of trajectories. It's much harder than compact sets in R. So luckily we have a criterion, which is Aldo's criterion, that is a probabilistic version of the Arzela-Ascoli theorem. for compactness of families of functions. Basically, what we want to say is that the projections are living inside a compact set, and that the oscillation, this is the modulus of continuity, it has a prime here because we're talking about continuous that allow for jump. So we want to make a small modification of the usual supremum that we take across a certain interval. But as long as the trajectories do not oscillate very much, we are in good shape to use the Aldous criteria. And in case we have checked these 2 points, we can say that there is a convergence subsequence, and we can start looking for what is how can we characterize these limit points. So now it's when we turn to Martingale problems. Martingale problems are a nice way of characterizing a certain class of limit points. So it really boils down to the following fact, that if you have a process that satisfies, well, it's continuous, first important, it is continuous, and satisfies this is somewhat, this is kind of a Dynkin formula for the function f. And the function here is just a function that has two derivatives, two continuous derivatives. If this is a local, if this strange formula here is a local martingale for all f, so that's actually a Brownian motion. That's how we should read this result. A Brownian motion can be disguised in these formulations of, if we can write these things and they are martingales, so, or local martingales, so this is a Brownian motion. That's the essence of martingale problems. And actually, we can make more sense of this if we recall the theorem from Lévy, which tells us that the unique continuous real-valued local martingale that has a specified quadratic variation is the Brownian motion. So just to complete the relation, let's take f of x equals x. What this gives us is that m of t minus m of 0 is a local martingale. The second derivative of this function here is 0, right? So m of t minus m of 0 is a local martingale, so the process mt itself is a local martingale. More, if we take f of x equals x squared, then what we find is that mt squared minus m0 squared minus t is a local martingale. And this means that the process is a Brownian motion because we can apply the Lévy theorem. So I want to show you a bit more of, do a little bit more of gymnastics with you, exercise our maths, basically proving this theorem from Lévy. So we already know it's continuous. So all we need to do is show that the increments are independent, normally distributed, and with a certain variance. So what we want to show is these two statements. And we're actually going to show the two at once if we prove that the expected value of these values, of these exponential martingales, multiplied by an indicator function for any measurable, fs measurable set, if they open independently as the product of the probability in A times the value of the characteristic function of these increments. So the proof is follows by an application of Ito's formula. Basically, what we do is take now multiply both sides by e to the minus I lambda ms times the indicator function, so that we can obtain in this side here indicator function of A, and here is ei lambda mt minus ms times the indicator function of A. These objects here, after we take expectation, do not matter anymore because it's a martingale, so the expectation goes to 0. Here, what we have, that's actually not upstairs, but downstairs. So let me close this parenthesis here, right? So if we take expectations, we end up in this formula, and we know how to solve this these integrals because it's a very common differential equation. So we know that that's actually true, and we have proved that's the essence of the proof, and you can find more details on that on Karatza's book. So, right. So to conclude, I'm almost out of time, but I want to give you the picture, the overall picture of how particle systems give rise in the limit to solution of stochastic differential equations, and how we are employing Dynkin Martingale's tightness arguments and Martingale problems to complete this picture. So basically, Martingale problems are the link between these two objects. First, the particle systems give us a family of martingales. I'm taking here the function f of x equals x. So we have some basic martingales. We could be also looking at certain projections. But once we have established that these families are compact or pre-compact, are tight, we can take a subsequence, and typically these limits will be continuous. So now what we have here is a continuous martingale, or local martingale, continuous. And when we test for the square, we can actually know what's the behavior of the variance, and using a more refined version of the problems, of the martingale problems, we can represent these martingales as stochastic integrals with respect to the Brownian motion. So that's basically it. We are going to combine these two equations into this integral formula that is the solution of stochastic differential equation. So that's what I want to tell you in more detail in the next two lectures. But the next lecture we'll concentrate also on the problem of constructing particle systems, and we'll see that martingales also play a role in helping us do that. So for your attention, I thank you very much.
Yes, thank you very much for the nice talk. Is there any questions from the audience? Let's see. So if you can't speak, you can also type in the chat. Yes, please ask.
Can you hear me?
Yes.
Maybe now you can see me as well. Hello.
Hi.
Yeah, so I wanted to ask, I think it's probably more about this tightness criterion. So I guess the point is you want to prove that there's some kind of limiting, let's say, measure. So is what you're doing effectively by this tightness criterion proving that you have some sort of like relative compactness, and then you're checking that all of the subsequences have the same limit, and therefore the limit must be the thing that you're
exactly.
Okay.
We separate the study of convergence in two. First, we prove it has a limit. If it doesn't have a limit, then it cannot converge, right? The first question is whether it has a limit. We separate that in the criteria for compactness. So tightness is a form of compactness for Polish spaces.
Yeah.
Right. So once we know it's tight, we can start investigating what are the limit points. So we separate the questions. Actually, most of the challenge is really in the proof of convergence after we have tightness. But tightness is a big thing.
Yeah. So I guess in the context of Kipnis-Landum, you're really wanting to take hydrodynamic limits. So you're kind of rescaling space and time as well. So you're checking you're checking this for trajectories on the Skorohod path space.
Yes. So yes, there is an art in choosing the metric that you're studying. The space of probability measures has many interesting metrics. There is the Lévy-Prohorov metric, Wasserstein metric. You can name it, right? Total variation distance is very interesting for cutoff, for instance, or other investigations. So here is, it's also related to the Skorohod topology. Exactly. In D, we're going to put the Skorohod topology, but the space is going to be the space of measures with a certain metric. So there is the art also of choosing the metric for the empirical measures that we investigate. Right.
I see. Thank you.
Okay, is there any other questions? Okay. If no, I have a question to ask. So I want to ask about the Dynkin Martingale.
Right.
Is there any Lyapunov type criterion with that?
Right. The the Lyapunov functions that you use, right?
Yes.
Will depend very much on the value of this prediction here. So because otherwise it's not exactly a Lyapunov function yet that serves our purposes.
Mm-hmm.
So if we have a specific sign here, for instance, if we know that LF is less than 0, then we are in good shape, right? To say that our process is a super martingale, and we can employ this as a Lyapunov function, right? To evaluate the evolution of the process, to bound it inside a certain region, obtain some sort of compactness, right?
Yes.